Hello, my name is Giacomo, and today I'm excited to present you our work on the limitations that transformer language models face when learning compositional tasks. This work was carried out at IBM Research Zurich in collaboration with ETH Zurich and MPI Tübingen. In particular, in this work, we focus on algorithmic tasks, which can be naturally decomposed into atomic operations. One example of such task is step-by-step multiplication that can be directly decomposed into two different atomic primitives. Digit multiplication, which consists of multiplying a number with a single digit, and addition. Other than using existing benchmarks, we also introduce a new family of synthetic algorithmic tasks based on pointer execution. One of them is pointer execution next, or PEN for short. In PEN, the goal is to chase a pointer by matching tokens in an input string, while outputting the right neighbors of the matched tokens. In particular, starting from the first element, we output its right neighbor, which is the first atomic primitive of the task, and then proceed to find a match in the input sequence, and move our virtual pointer, which corresponds to the second atomic primitive of the task. Once again, we output the element to the right of the pointer, and then proceed like this until there are no further matches in the input string. After defining the benchmarks, we outlined 4 different hypotheses to characterize more formally the different regimes of sample efficiency in learning to compose known primitives operations. Firstly, we have H1, which is verified when learning the composition of primitives requires a constant number of samples. In H2, the composition is learned with fewer samples than those required to learn the most difficult subtask. In H3, the composition is learned with fewer samples than the sum of those needed to learn every subtask. And finally, in H4, the composition is learned with a complexity greater than H3. Ideally, we would expect a model which is able to take advantage of the compositional structure of the task to learn it efficiently and fall somewhere between H1 and H3. However, our empirical evaluations show that this is not the case. In these experiments, we train from scratch llama models on the PEN task, together with subtask which makes its primitives observable. If we compare the amount of samples necessary to learn the subtasks with those required to learn their composition, we can observe that the latter requires more data than that required by the most expensive subtask. This renders hypotheses H1 and H2 unlikely. Learning the composition also requires more data than the sum of the individual subtasks, which renders hypothesis H3 unrealistic as well. Eventually, the composition can be learned, but this requires an exponential number of samples, which is well within the H4 hypothesis. The conclusion that we can draw from these experiments is that transformer language models can learn compositional algorithmic tasks, but they are extremely inefficient in doing so, because they cannot reuse and properly compose the information provided by each of the subtasks. The same observation also holds for every dataset that we designed, as well as for datasets that were used in previous works to investigate compositionality in LLMs. In addition, we also benchmarked pre-trained LLMs, such as GPT-4, in our novel dataset. We observed that in-context prompting with few samples is also unreliable and fails to solve these new tasks, making our hypothesis H1 also unrealistic for current state-of-the-art models. This happens despite providing considerable effort in the prompt engineering, such as task and subtask descriptions, chain of thought, and code generation, which increase the task accuracy and the performance of the model in tracking the pointer in the input string, but to a very limited extent. The same trend was also observed in other state-of-the-art pre-trained models, such as Gemini Pro. To sum up, the main message of this work is that transformer language models are inefficient learners of composition of tasks, requiring more training samples than the sum of those required to learn each task individually. That concludes my presentation for today. If you are interested in our work, please check out our paper and open source code implementation. Thank you for watching, and see you in NeurIPS.